Swayam Prabha. Digital India. Educated India.
Now, to draw a performance equation for a batch reactor, we know the first equation, which demonstrates how the cell concentration will change with time, or the growth rate of the culture in a batch, which is equal to mu times Cx. Let's call this as equation 1. So if we want to determine the batch time, we can integrate. Let's assume the starter culture concentration is Cx naught and the batch time is T. So then if we integrate equation 1 with the boundary conditions of x naught, Cx naught and Cx for the biomass and T naught for the time. So then your batch time, which would be T minus T naught is generally 0. Then Rx, which is given in equation 1, has been further substituted as mu times Cx, as again shown in equation 1, and you apply the limits after integration. So this is how you can calculate the batch time. Now, T naught is generally equal to 0 when we assume that there is no lag phase. But if there is a lag phase, so you remember last class we were talking about the lag phase, in which there is a phase which is called as the acclimatization period, where the cell division is not happening. So if suppose there is a lag phase and it is of some time T naught, then the batch time would be a difference between the time of harvest to that T naught. That is why it is given in equation 2 as T minus T naught, where if there is no lag phase, then T naught can be substituted as 0. Now, if you see equation 2, and if we make a plot of 1 by Rx versus Cx. So if you remember the previous equation, it is dCx by dt equals to Rx, isn't it? Rx was your growth rate. So we can write it applying integration as equation 2. Now, with this equation 2, if you make a plot of 1 by Rx versus Cx, then it looks like this. And if this is your harvest time, where your final concentration is Cx, and this was your beginning, which is your Cx naught. So can you see that it takes a U-shaped curve? Now, in order to understand why it is taking a U-shaped curve, let's see. If Cx is very less, then the growth rate is less initially. As the biomass is getting produced, because the growth rate is improving. So your 1 by Rx during the log phase comes down till the culture is growing, and then suddenly, after depletion of the nutrients, the 1 by Rx will go towards 0. So for a batch, if starting was Cx naught and the final is Cx, and if you make a plot of 1 by Rx versus Cx, then if given these limits, the area under this curve with these limits will demonstrate something. What will it demonstrate? It will demonstrate the batch time as given in equation 2. So now, biological reactions or cell formation in a reactor, it is termed as an autocatalytic reaction, where the biomass is said to be catalyzing further production of the biomass, as shown in equation on top. So S stands for substrate. So S is combining with the biomass, which means the biomass is consuming the substrate and producing more biomass. So the rate of reaction is slow at the start. As the concentration of X, which is the catalyst here, keeps on increasing, the rate of reaction also keeps on improving, and until it reaches the maximum rate. So if you can see the schematic shown here, it demonstrates a batch kinetics in which the initial biomass concentration, which is the concentration of your starter culture, Cx naught, when put in the medium, and at the harvest, which is the maximum cell concentration, is Cx. So a plot of 1 by Rx versus Cx is shown to with growth, it is increasing the biomass, it reaches its maximum, the rate, and then it suddenly goes to very high value, which means nearly going to 0. So as the substrate depletes, the toxic products accumulate and it will decrease the value of Rx, and therefore the 1 by Rx value suddenly increases. So as I said in the earlier plot, the area under this curve, which is shown here as a shaded region, is what will give us the batch time, the time in which the biomass concentration achieved becomes Cx. So this technique can be used to compare the efficiency of different reactors. Different in the sense, efficiency especially when you want to compare a batch reactor with a continuous reactor, or a combination of reactors. We will take an example as we move ahead. Now, Monod's parameters, if you remember Monod's equation, in order to make the Monod's model for a system, we will have to define the values of these constants in the Monod's model, which we call as the maximum specific growth rate and the Monod's saturation constant Ks. How to determine the value of these? You can use batch culture to find the value of mu m and Ks. But that may not be the right estimate. We will see how we can do, and once we take the continuous fermentations, we'll be talking about the limitations of this procedure as well. But for a guess, for a rough guess or for initial guess, people do use this technique. So in which if you do a rearrangement or you do some experiments where you collect the specific growth rate values at different substrate concentrations, and you make a plot of 1 by mu versus 1 by S, then you will get an inclined straight line, which we call as Lineweaver-Burke plot. Now, you must have heard about the Lineweaver-Burke plot during calculation of the kinetic parameters in enzyme kinetics following Michaelis-Menten equation. So do you remember Michaelis-Menten? Michaelis-Menten was the rate of enzymatic reaction, Vmax, multiplied by S versus Km plus S. But here it is the rate of enzymatic reaction, and here it is specific growth rate. So direct implementation of Lineweaver-Burke plot, which we generally use in enzyme kinetics, which we call as 1 by V versus 1 by S plot, may not give the two representation of the monods model parameters. The reason being, the initial rate of reaction is always zero for cell cultivations, unlike enzyme reactions. There is an extra Cx term on RHS in monods rate equation, which is not present in the Michaelis-Menten equation. So if you see equation 1 and equation 2, your equation 2, where we have given for growth rate dCx by dt, it is equals to mu max. They have substituted monods model, which is Cs by Ks plus Cs multiplied by mu max, and this Cx term has come from the LHS, which was because mu is equals to 1 by Cx dCx by dt. So this Cx has been taken to the other side. So if you now compare Michaelis-Menten equation, which is the rate of reaction, is the maximum rate multiplied by the substrate concentration by Ks plus Cs, but there is an extra Cx term which is not there in the Michaelis-Menten equation. So this is how they are different. Now in monods equation, there are certain assumptions which we take. Like being a controlled bioreactor system, we assume that the fermentation is running at the optimum temperature and pH, which is being continuously maintained throughout the cultivation period. Hence, the effect of temperature and pH is negated, or it's not taken into account on the specific growth rate. There is only one substrate which is limiting the specific growth rate. However, apart from substrate, there are other factors, physical and chemical, which are also having effect on the specific growth rate of the culture, like medium pH, temperature, oxygen supply, where the significance of each of these factors may differ from organism to organism. Like for example, psychrophiles. Psychrophiles, these are organisms which generally grow at temperatures less than 20 degrees C or at lower temperatures. Or mesophiles, where the optimum temperature ranges between 20 to 50 ambient temperatures. Thermophiles, which only survive at very high temperatures. So then, depending on the organism, the effect of temperature may vary on the kinetics of the growth kinetics of the culture. Now, above the optimum temperature, the growth rate would decrease and thermal death rate may begin. Let's talk about cultures, mesophiles. They grow at ambient temperatures. So, at very low temperatures, you will find the growth rate slow, and at very high temperatures, suddenly you will find that the cells begin to die because the cell starts lysing and the internal components starts getting denatured. So then, to take into account the thermal death rate as the temperature is high, where then the apparent growth rate will have to be a club of the actual growth rate with the simultaneous death rate. So here, if you observe equation 1, it is taking into account the growth rate and the reduction due to the death rate. So the net specific growth rate is given as a difference between the growth rate, the specific growth rate of the culture, minus the death rate of the culture, the specific death rate of the culture, which is termed here as Kd. Now, growth rate increases to its maximum with increase in temperature to T optimum. So, the plot may be more like a hill, where you'll observe that the growth rate of the culture will increase as the temperature is increased. This behavior is generally found to follow a well-known model which is called as Arrhenius equation, which demonstrates the effect of temperature on the growth rate of the culture. And the thermal death rate after that optimum temperature, if we continue to increase, then you will observe that the growth rate of the culture will start, which is the net, will start decreasing, which is due to the thermal death rate, which can, again, it is analogous to the Arrhenius equation. The difference is that the death rate would be now having a negative sign, and it is demonstrated as Kd, the specific death rate. Now, Ed and Ea, I hope you remember Arrhenius equation. So Ea is your activation energy for thermal growth, and Ed stands for the activation energy for thermal death. And it is observed that Ed is generally higher than Ea, because as the temperature is increasing, so beyond the optima, it will start decreasing. So the activation energy for thermal death is much higher than the activation energy required for growth. So thermal death is more sensitive to temperature changes than the microbial growth because of this increased factor, Ed. So now, how environment conditions affect growth kinetics? Product formation, your yield coefficient, they are also affected by temperature, and hence temperature should be optimized to maximize the yield. As the temperature increases beyond optimum value, the maintenance requirements and therefore the value associated with the maintenance coefficient of the culture increases. As a result, your Yx by S, which is your yield coefficient, starts decreasing. So if you remember in the last class, we talked about in what all different aspects the substrate gets consumed. It not only gets consumed for growth, but it also gets consumed for endogenous metabolism, which is a club of the maintenance energy. So when the maintenance requirements are high, there is a large amount of substrate also getting utilized for the maintenance requirements. So your net yield coefficient, which is a club of all these factors, the yield coefficient for the growth will start decreasing. The diffusional rate should be considered, which might become rate limiting step as bioreaction rate increases with temperature. So now, as we know that the growth rate is a function of temperature, now as the temperature increases, the growth rate will keep on improving till it reaches its optimum temperature, desired temperature. Now, as the growth rates are improving, then the rate limiting step could become the rate at which the substrate is being made available to the cell, where diffusional limitations have to be considered. pH affects the activity of the enzymes and therefore the growth rate of the culture. In most fermentations, the pH can vary substantially depending on the nature of the nitrogen source. So generally, nitrogen source are provided in the form of nitrates or ammonium salts. So production or utilization of organic acids like amino acids, or evolution or supply of carbon dioxide, all these factors may play a role in the change in the medium pH during fermentation. Now, dissolved oxygen as an important substrate in aerobic fermentations and can become limiting substrate as it is the sparingly soluble component in the fermentation broth. At high cell concentrations, the rate of oxygen consumption may exceed the rate of oxygen supply inside the reactor, which can then lead to oxygen limitations. Specific growth rate in that case starts getting affected by the dissolved oxygen concentration as a saturation kinetics, which means that rather than substrate which is readily available, carbon, nitrogen, medium components in the medium, if it is oxygen limited, it will follow this saturation kinetics in terms of oxygen concentrations in the medium. Now, below a critical concentration, the growth or the respiration follows first order kinetics with respect to the dissolved oxygen concentration, and above the critical concentration, the growth rate is independent of the dissolved oxygen. So if you see the plot, your critical oxygen concentration will be somewhere here. So above this, you may observe, you may call this as QO2, your specific growth rate or specific product formation rate, which is biomass here with respect to your oxygen. So here you will observe that the growth rate of the culture will become independent of the concentration of oxygen above this critical value, but below this critical value, it varies mostly linearly. So generally, oxygen is introduced into the fermentation broth by sparging air. Now, oxygen has to be transferred from the gas bubbles to the cells, which can get limited by the oxygen transfer through the liquid film which is surrounding the gas bubble. So your equation 1 given on the slide demonstrates the rate at which the oxygen is getting transported to through that liquid film. So dCl by dt is your rate of transfer of oxygen, which is given by KLa. This is called as volumetric mass transfer coefficient. And the second term is the driving force, which is the difference between the maximum solubility of oxygen under the given conditions of the fermentation, and Cl is the concentration of oxygen in the broth, in the bulk. So this equation is called as OTR, which is the oxygen transport rate equation. Similarly, the rate at which the oxygen is getting consumed in the fermentation broth can be given as QO2 multiplied by X, where what is QO2? Your QO2 stands for the specific oxygen demand of the culture, which means the amount of oxygen consumed per unit biomass per time. So to understand oxygen uptake rate as QO2, which is specific oxygen uptake rate. So if we convert it into oxygen uptake rate, we need to multiply it with the biomass so that it becomes oxygen uptake rate. The rate at which oxygen is getting consumed for growth, which can be equal to mu x by yx by O2. Now what was yx by O2? It can be written as dx by dt by dO2 by dt, the amount of oxygen which has been consumed for the growth. So if you multiply, if you need to know the amount of oxygen consumed, the rate at which it is getting consumed for growth, you can write it as dx by dt by yx by O2. Now this dx by dt is again substituted as mu times x, and then you get your equation 2. Now when oxygen transfer is rate limiting, it means that the rate at which the oxygen is coming inside the reactor is exactly equal to the oxygen demand, which means the rate at which the oxygen is getting consumed in the reactor. If this is happening, there is no oxygen accumulation taking place inside the reactor. So in that case, your oxygen transfer starts becoming rate limiting factor, and your growth rate can then be made a function of the oxygen transfer, taking a form of equation 3 here, where your dx by dt can be given as yield coefficient multiplied by the oxygen transport rate, which is KLA multiplied by C star minus CL, as given in equation 1. We'll be taking oxygen transfer much more in detail when we're talking about mass transfer operations in bioreactors. So redox potential, this also affects the extent of oxidative and reductive reactions in the fermentation. It is said to be a complex function of dissolved oxygen, pH, and other ion concentrations, like reducing or oxidizing agents if present in the medium. So if you see equation 1, it is one of the ways in which the redox potential has been demonstrated, where EH is the electrochemical potential of the fermentation medium. The redox potential of the medium can be increased by passing oxygen and can be reduced by nitrogen. So if you see the term PO2, which stands for partial pressure, your redox potential can be improved as the partial pressure can be increased by passing in oxygen and can be reduced by removing oxygen by purging in nitrogen. Dissolved carbon dioxide concentration also has a profound effect on metabolic functions and growth rate, especially in case of plant cells or animal cells. And very high concentrations can also be toxic. Then ionic strength of the medium. This can affect the transport of certain nutrients in and out of the cell, its metabolic functions, solubility of nutrients like that of dissolved oxygen. So then ionic strength can be defined as given in equation 2 for the medium, where Ci stands for the concentration of a particular ion and Zi will be the charge of that ion in the medium. So it is a club of all the ionic species and their associated charges which make up the ionic strength of the medium. High substrate and product concentration and sodium chloride can lead to reduction in water activity and high osmotic pressure.